Hi everyone, my name is Paula and I'm a third-year PhD student at Queen Mary University of London. And today I will be talking about Gaussian process regression and an application it has in radio cosmology. So let's start by talking about the large-scale structure. This describes how matter is structured in our universe on a large scale, and studying it can tell us a lot about the universe, such as lambda CDM model parameters, possible alternatives, the physics of dark components, tests to general relativity, and much more. So we are very interested in observing this large-scale structure. And one way of doing it is using galaxy surveys, because galaxies are a good bias tracer for the underlying dark matter distribution in the universe. So galaxy surveys can help us trace the large-scale structure, but you have to resolve each individual galaxy, so it can be expensive and time-consuming. And an alternative is H1 intensity mapping. So after reionization, most of the neutral hydrogen in the universe can be found inside of galaxies. So neutral hydrogen, or H1, is a good tracer, a good bias tracer for the underlying dark matter distribution, the same way that galaxies are. And with intensity mapping, we're not trying to resolve each individual galaxy using their H1 content. We're just trying to observe the H1 intensity across the sky. And where there's more intensity, that means there's more matter present. And where there's less intensity, that means there's less matter present. And so this is very good for mapping large areas of the sky very quickly, which is great for large-scale structure surveys because we want to observe as much of the large-scale structure of the universe as possible. And this type of survey has very good frequency or redshift resolution, but it does suffer from a low angular resolution because of how the telescope operates. But a much bigger issue is the foreground problem. So a foreground is any signal we detect that is not our desired H1 cosmological signal. And in our case, we have several astrophysical foregrounds that dominate over the H1 or 21 centimeter cosmological signals, such as galactic synchrotron, point sources, and galactic and extragalactic free emission. And these are much brighter than our cosmological signal, so they dominate over it. As you can see on this plot on the left, I'm plotting the temperature as a function of frequency of different signals. And the solid lines are different simulated foreground components. And you can see that these foreground signals are very smooth in frequency, but also very bright. And the black dashed line is the H1 cosmological signal. And you can see this is not smooth in frequency because it's tracing the matter in the universe, but also it's very faint. So if we don't get rid of these foregrounds, we're not going to be able to access this cosmological signal that we are very much interested in. So the motivation behind this project was that Gaussian Process Regression, or GPR, has already been applied as a foreground removal technique successfully in the context of the epoch of reionization, so at high redshifts. And we wanted to ask, how would GPR perform in the case of low redshift single dish intensity mapping? How does it compare to other widely used foreground removal methods, such as PCA? And could we use it for future intensity mapping surveys, such as the square kilometer array? So essentially, we wanted to see if GPR was a feasible foreground removal method for doing large-scale structure surveys with intensity mapping. So let's talk about what a Gaussian process is. So a Gaussian process is just a Gaussian distribution defined by some mean function m and some covariance function k. And these are functions of frequency because our data is a function of frequency. So if we have some random variable f that we say can be described as a Gaussian process, it will be defined by some mean function and covariance function as like this. And the covariance function is typically, though not always, itself a function of three hyperparameters. So you have the length scale, which describes how correlated the data is. So if our data is a function of frequency, the length scale describes how correlated the data is as a function of frequency. And the variance describes the overall amplitude of the signal, and the spectral parameter describes how overall smooth the data is. And for the length scale and variance, we want to find the best fitting values. But for the spectral parameter, we want to choose the best value, because different choices for this parameter will actually change the functional form of the covariance function. So we need to make sure we choose the one that gives us the best model. So then what is Gaussian process regression? So Gaussian process regression starts by assuming you have some data D that can be described as a Gaussian process with some mean function m, some covariance function k. And the mean function we can usually take to be 0 because you can just subtract the mean from your data. So using this, we can make predictions for what the data would look like at some new frequencies that we haven't observed at, using this joint probability. And essentially what we're saying is, given this data we already know, and the fact that we're describing it as a Gaussian process, what would the data look like at new points? And in our case, we assume that our data and each of its components, such as foreground, the H1 cosmological signal, and noise, can be described as a Gaussian process. And we are using futuristic SKA-like simulations. So our data is composed of the foreground signal plus the H1 or 21 centimeter signal plus the noise. And so our data's covariance function K is also going to be composed of the covariance function of each of these components added together to reflect what the data looks like. And the foreground is split into the smooth and polarized foregrounds, as I will explain. So the smooth foregrounds here, I'm showing the signal temperature as a function of frequency, and the different lines are just different pixels I've chosen to show from the simulation. And you can see that the smooth foregrounds are very correlated in frequency, so they should have a large length scale. They're very bright, so they should have a large variance, and overall they're very smooth, so they should have a large spectral parameter. And the polarized foregrounds come about due to some systematic effects of how the smooth foregrounds interact with your telescope. So these become a little bit less correlated in frequency, so we expect a smaller length scale, and they're a little bit less bright, so we expect a smaller variance, but they're overall still very smooth here, so we expect a large spectral parameter still. And now for the 21 centimeter signal, or H1 signal, we can see that the data is not very correlated in frequency at all, so we expect a very small length scale. The amplitude is also very small. The signal is not very bright, so the variance should be small. And overall, the signal is not very smooth, so we expect a small spectral parameter compared to the foregrounds. To actually find the best fitting hyperparameters, we use our data. So we're assuming that our data is Gaussian and that the noise is also Gaussian distributed. So we can calculate the marginal likelihood or evidence analytically, and we can find the choice of hyperparameters that maximizes the evidence using something like gradient descent, for example. And we do this optimization procedure where we find the best fitting length scale and variance for different choices of the spectral parameters, so for different covariance function models, and then compare the evidence using a base factor analysis to find what the best choice for the spectral parameter is. And you can use this instead of gradient descent with nested sampling, for example, which just gives us a much more robust estimate of the evidence. So we'll be able to choose the hyperparameters better. And it also yields posterior distributions for the hyperparameters. So here on the left, I'm just showing a result for obtaining the posterior distribution of our covariance function hyperparameters using nested sampling. You can see that it can obtain the posterior distributions very well. And the dotted gray line is the result using gradient descent. So they agree very well in our case, but gradient descent gives point estimates for the hyperparameters, whereas with nested sampling, we actually have an uncertainty on our estimates, which is very useful. So it's better to use nested sampling because it's overall more robust and gives us uncertainties. So we did this with our data and we obtained the optimized covariance function. So for the 20 centimeter signal, we found that a spectral parameter of 1/2 was the best choice, and this is called the exponential function. We found that a small length scale and a small variance were the best fit as expected. And then for the polarized foregrounds, we found that a radial basis function with a spectral parameter of infinity is the best covariance function model with a medium length scale and variance. And then for the smooth foregrounds, we also found that the radial basis function was the best fit, but with a much larger length scale and variance, because these are the brightest foregrounds and the most correlated in frequency. And here you can see these best fitting covariance functions plotted in frequency. So then how do we remove the foregrounds using this? Well, we start by predicting them. So we take our data that we know and its mean function, which is just 0, and its best fitting covariance function, which is just found. And we use this to predict what the foregrounds look like in our frequency range. So before, when I described the GPR, I said that we wanted to use it to find new data points. But here, we're not interested in new frequency ranges. We're just interested in our frequency range, but we want to isolate the foreground signal so that we can remove it. So you can see that to do this, we do need our full covariance function, but we also isolate just the foreground covariance function to get out our foreground signal prediction, and then we remove it. So to summarize how we do foreground removal with GPR, we start by assuming that our data can be described as a Gaussian process with some covariance function K. We find the best fitting covariance function using, for example, nested sampling. And this is the hardest part and the most time consuming. But once you've done this, you just use your data and its covariance function to predict what the foregrounds look like, and then you remove this foreground prediction from the data. And if you're interested in running this pipeline or learning more about this, we have some publicly available code on GitHub that is easy to install. There's lots of introductory notebooks that run through this pipeline step by step using some simulations that are also in the GitHub. And they run through how you can do this with gradient descent or nested sampling. So if you're interested in learning more about this, check that out. And now I'm going to talk about our results. So first, we start by ignoring the polarization leakage. This is the best case scenario. So we just have our 20 centimeter signal and our smooth foregrounds and some noise. So the black solid line is the true H1 power spectrum. And this is what we want to recover. And the GPR results are in green. And we show also results obtained with another widely used foreground removal method, principal component analysis, which requires you to choose a number of components to remove from your data. And this removes the foreground. So we show here PCA with n equals 2 and n equals 3 to have a broad comparison. And the bottom panel shows the percentage residual difference from the truth. So we want this to be as close to 0 as possible. The pink vertical line shows the K-bin below which GPR diverges to above 10% from the truth. So we say that below this K-bin, GPR fails to recover the truth. But you can see that PCA n equals 2 is actually able to recover smaller K-bins than GPR, so it might be able to access larger scales. But you can also notice that on large scales, PCA n equals 2 is really under cleaning, which means that there's probably a lot of residual foregrounds left. And having these sort of residual foregrounds is really going to boost your power spectrum error. So we really want to avoid this. So we might look at PCA n equals 3 instead, but you can see PCA n equals 3 does not perform that well on small scales compared to GPR and PCA n equals 2. You can see GPR performs very well on small scales. So overall GPR gives us a sort of best of both worlds. It doesn't underclean on large scales like PCA n equals 2 does, and it performs better on small scales than PCA n equals 3. It's also interesting to look at the radio and transverse components separately. So for the radio power spectrum, GPR performs very well. It recovers the full K parallel range within 10% residual, and it performs better than PCA, especially on small scales. For the transverse power spectrum, this is not the case anymore. GPR does not perform as well. It does not recover the full K perpendicular range, and especially on the middle K perpendicular range, it performs worse than PCA. It does perform very well on the smaller scales, but because of the angular resolution of our telescope, there is essentially no information here of interest, so this is not very useful. But overall, GPR performs much better in the radial than transverse direction, which makes sense because we're mostly using frequency information. Our covariance function is a function of frequency, so is our mean function. So the GPR really takes into account a lot of line of sight information, more than it does transverse to the line of sight information. So this makes sense that GPR performs better in the radial direction. Now we try including the polarization leakage and see what happens. And you can see that the K-bin at which GPR fails is now larger, meaning that we cannot access the same larger scales as we did without polarization leakage. So GPR seems to suffer from the inclusion of polarization leakage and is not as obviously performing better than PCA. It's still performing really well on small scales, better than PCA n equals 7 on some scales, but it does seem to suffer from the inclusion of polarization leakage, which we ran some tests on, and we believe it's because GPR finds it hard to differentiate the polarization leakage from the smooth foregrounds and from the H1 cosmological signal because they get confused. And so we also wanted to test if there was any sort of bandwidth or redshift dependence with GPR. So by bandwidth, we just mean the frequency range of the data. So what we did, we cut the data in half along frequency, and we compared both halves with each other and also with the full frequency range or full bandwidth case. So here we are looking at the high frequency, low redshift half. And you can see here that GPR performs better than the full bandwidth case because the k-bin at which it fails is larger. It's now k equals 0.1. And it also overall performs just much worse than PCA on these small scales. You can see it's performing much worse than PCA, n equals 4. So overall here, GPR performs worse than PCA and worse than the full bandwidth case. Whereas in the low frequency, high redshift half, so the other half of our data, GPR actually seems to perform really well. It can recover larger scales than it did in the full bandwidth case. And now k equals 0.08. And in a full bandwidth case, it was k equals 0.09. And it also seems to perform better than PCA because both PCA cases are under cleaning our data, which is going to lead to a boost in errors, whereas GPR still recovers the small scales really well without this sort of under cleaning. So here we see the opposite. We see it performs better than PCA and it performs better than the full bandwidth case. So we wanted to test this because of a study last year led by Ian Houghty, found that GPR prefers smaller bandwidths than larger bandwidths. But here we did not find conclusive evidence of this, possibly because our data is quite different. It's much lower redshift than theirs. However, we did find that GPR seems to prefer the higher redshift case. And this is interesting because in the higher redshift, the foregrounds are actually brighter. So this could be because it's easy to differentiate the cosmological signal from the foregrounds when they're more different, when the foregrounds are brighter. But it's definitely something to look into in the future to try and figure out how to optimize the performance of GPR for future surveys. So the key takeaway here is that it is indeed possible to run GPR as a foreground removal technique in the case of single dish, low redshift, H1 intensity mapping. So for example, for large scale structure surveys, and we find that GPR performs better in the radial direction than in the transverse direction. And it also performs better in the absence of polarization leakage, and polarization leakage seems to make GPR foreground removal more difficult. It's also interesting to note GPR performs better at high redshifts than at low redshifts. A really important thing to note as well is that for PCA, we constantly needed to change the number of components removed from the data, depending on our bandwidth size, whether we included polarization leakage or not, for example. And this can be a little bit of a fiddly parameter because we don't know the truth with real data beforehand. We don't know how many components to remove exactly. So we have to use the data to find the best number of components to remove without really knowing the truth. So this can be a little bit of a tricky parameter to choose. And GPR does not require this type of fine tuning. It finds the best fitting covariance model given the data using, for example, gradient descent or nested sampling. So this is an advantage that GPR poses over foreground removal methods that have this sort of parameter that you have to fine tune. And again, our code is available on GitHub if you want to learn more about the pipeline, and I'm happy to answer any questions. Thank you for listening.